Okay, so we've just completed setting up a one-dimensional model that simulates the hydraulic head along a radial distance between an injection well and a constant head boundary out at 1,000 meters away. This was described in an earlier video, and the setup where we ended that video is shown right here. We have a display of the hydraulic head as a function of the radial distance, and the green is the analytic solution. The blue is the numerical solution. And if we come up here to take a look at the geometry, you can see it's just this 1D geometry that is really fairly simple. And so what I'm going to do is modify this model and include a 2D and a 3D version of it. And even though the problem is really just 1D, I'm going to use this as a way to illustrate how to set up models in 2D and 3D. So first we'll make a 2D model. This will be axial symmetry. We'll revolve it around the 2D vertical cross-section. And so to do it, we'll create another model within this file. So we go up here to the top of the model builder, and we right-click and we add another model. And this will be 2D axisymmetric, and we'll use Darcy's law. It will also be stationary. And here's the model. Now, just to keep things straight, I'm going to go up here to this first model and rename it 1D. And I'm also going to collapse it down so it doesn't take up much room. And I'll rename this guy 2D model. Okay, so the procedure is much the same. We're going to put in some variables, and we'll use the same file that we used previously. So we import them, and the next step is to put in a geometry. And in this case, instead of a line, it'll be a rectangle. This aquifer is 1,000 meters in radius and 10 meters thick. So the height is 10, and the width will be 999.9. And the position of the corner will be at 0.1. And so if we build that, that's what the aquifer looks like. So let's zoom in here and zoom in some more. And so here's this is what we're thinking the well is right here. It's out at a radial distance of 1/10 of a meter. And this is axially symmetric, so this cross-section that we've created is revolved around this axis of symmetry. Okay, so we go to Darcy's law, and this will be the same routine that we've done before. We need to give the fluid properties, and they'll be the same properties that we used previously. So we'll put in 1,000 kilograms per cubic meter for the density and 0.001 for the Pascal seconds for the dynamic viscosity. And the hydraulic conductivity, we've imported that in the file, and we'll call it K. And the user-defined porosity that we'll give it is just 0.1. Okay, so all this stuff, these defaults will keep, and we have to put in boundary conditions. So the conditions will be the same, hydraulic head and inflow flux. So now to specify the boundaries, we zoom in here on this outer boundary, we select that edge and we click plus to add it here, and we'll again use the default for the inflow boundary. We select it, and we'll use well flux for the inflow boundary. Okay, so now we're ready to go to the mesh, and we'll just use the defaults. There's the defaults. This is really quite a coarse mesh, but let's just go ahead and give it a try. We can easily modify it later, but let's just try this for now. Okay, so now to run it, you see that when we added this additional model, we added another study by default. This is the study that runs the 1D model. And let's see, and this will be the study that runs the 2D model. So what we do is expand it, go here to stationary, and we have two physics in here. This one, DL2, is what we want to use. We don't want to run this, the 1D model. So we'll uncheck that. This is just going to run the 2D model. And notice, however, though, we could run both models at the same time. And in some applications, we may want to do that and couple the models together. But in this case, it's much simpler than that. We'll just run the 2D model, and so we'll go here and try it out. So I press that equal sign. It does the calculations and gives us the results. Okay, there we go. There are the results. And this is a 2D problem now, so we get as a default a 2D color flood display. And so there's the these are the pressures, and we have some low pressures here near the well that increase as we go further away from the well. Just like we did last time, we can change the parameter that's being plotted here, expand it, and here's the surface plot that's being shown, and there's pressure P2, so we want to change it to the hydraulic head, and there's the results in terms of hydraulic head. We can show the profile in hydraulic head, and we can do that along a line. There are a couple of ways that we can do that, but a nice way, it's fairly versatile, is to include a cut line. And so we'll go here to Data Sets, we'll go to Cut Line 2D, and we'll define a line that goes from point 1, a radial distance of point 1 to 1,000, and we'll just run this right up the middle at an elevation of 5. And we'll use solution 3, and here's what we got to do. This says solution 3. We go here, this is the data set from called solution 3, and it's from solution called solver 2, and I'll show you where that's indicated. There's solver 2 under study 2. So this is right now kind of confusing because there are all these numbered kind of generic names, but all of these names here can be changed, and we can set them up to be whatever we want, and that will help us keep track of what the different solutions are. So we can make those changes, and I would recommend doing that, but I'm not going to do it now just to save some time. We define this thing cut line 2D1, and so let's make a plot of the variable, the data along cut line 2D1. So in order to do that, there are two approaches. We could go up to results, right click, and add a 1D plot group. And we then right click and go to a line graph. And when we plot that line graph, we go up and select the data set, cut line 2D1. And we have to pick a variable then to plot, and we're wanting to plot hydraulic head. And there we go. So there it is. Now, one thing I should point out is there are two Darcy law physics in this file right now. One is labeled DL, and this one is DL2. So we could take a look at the hydraulic head from the previous model along with the hydraulic head from this model. This one is called DL2.H, and the other one is DL.H. So we see now this prefix right here that designates the particular model, allows us to refer to these different data sets from different models. So it gives us, it's actually quite powerful. It gives us a good bit of flexibility. One thing that it also allows us to do is compare the solutions. So we go back to the plot that we generated from the 1D solution, and we add another line graph, basically just repeating what we did down below, and we plot the data from the cut line 2D, and we want to go here and plot the hydraulic head. So here are the data from that solution, and let me plot it as a function of R, and make it a little bit thicker, and there we have it. So there's the comparison of the 1D solution, the 2D solution, and the analytical solution.